All right, 7.4 example 2. And I think this does help the understanding because the function gets a little more complex. So it's not quite as, there's a lot of weird, like the x was 1 and the y was 1 in the last example. This example, that won't happen. Right off the bat, I really do want to stress that students often make questions like A much more complex than they should be. Right? If we know that f of x is equal to 2x plus 5, then y equals 1 over f of x is simply taking what f of x is and substituting it into that equation. So, and I'm going to write that as 1 over f of x is equal to 1 over, and then I am going to put the square bracket just to try to help make that connection, the 2x plus 5, which was f of x. Now, this isn't a great way to identify kind of, or to leave, I suppose, but if you were putting it into your calculator, I would highly recommend, again, it's a good visual, and we'll do that on one of these questions. I want to talk through them first, that y1 we could put into our calculators 2x plus 5, y2 would be 1 divided by, in a bracket, 2x plus 5. You have to be really diligent with those brackets when your denominator is a little more complex like it is in this question, just to make sure your calculator understands that the entire expression 2x plus 5 is in the denominator of that. So to clean that up a little bit, I am going to say that 1 over f of x, it's weird to write that bracket, so I'm just going to write it as 1 over 2x plus 5. Now, B wants us to determine the equation of the vertical asymptotes. And I just want to identify that 1 over f of x has a vertical asymptote, and I'll just abbreviate asymptote here, when f of x is equal to 0. Always. That's one of those nice general statements in math that we can always say. And that's a really, really powerful thing. Solving for when a function is 0 is something you've done plenty of, so hopefully you're pretty comfortable with it. If f of x is equal to 0, then 2x plus 5 is equal to 0. When I subtract the 5 from both sides, I get that 2x is equal to negative 5. That means that x is equal to negative 5 over 2. Now, what's very important is that is not a point. That is a vertical asymptote. And what that looks like on a curve, I'll just put what that's equal to. That's negative 2.5. If we put that on a Cartesian plane, then what that would be is a vertical dotted line where everywhere on that dotted line, x is negative 2.5. Y is a bunch of different values. That's okay. But what that dotted line indicates is a line on the Cartesian plane that everywhere along that line, x is equal to negative 2.5. So that gives us a nice vertical line that the graph approaches but never actually touches. All right, now C is a little trickier. We're going to talk through it piece by piece, and there is a nice technique that is really what we have to take out of this. I'm just going to extend this a little bit so I can see it. I'm going to say that f of x is 2x plus 5, and 1 over f of x is equal to 1 over 2x plus 5, just so I have that in front of me as I draw these. Now, I'm going to draw these two functions, and this is certainly where, trying to make your graph a little bit accurate does help. The y-intercept of f of x when x is 0, y is 5. So I'm going to put that point up there. I'm just going to label it above. So that's 0, 5. The x-intercept, we actually calculated. The x-intercept is this, because the x-intercepts of f of x become the vertical asymptotes on 1 over f of x. So 2.5, trying to keep, a reasonable scale, I'm going to say that it's right there. And then because this is a straight line, I can connect those with the line. And I'm just going to kind of circle this in red. Now, I think if we talk about kind of the step-by-step procedure, I think step 1 is to draw f of x. Step 2 is to draw your vertical asymptotes. Step 3 is to draw or identify, same thing, your invariant point. And then step 4 is to draw 1 over f of x. Now that's a bit of a simplistic process, I suppose. It's certainly more complex than that, but I think that's the best place to start. And as you do more and more of these questions with help from your calculator, you will get used to some of the behaviors. And I do want to emphasize that in a pinch, you can pick 10 or 15 or 20, if you want to go overboard, points on f of x, and then just transfer them to 1 over f of x. And that is a really, really big benefit, that nothing more crazy is happening than, just as a quick example, and I want to do this really quickly, I'm going to do 1 over f of x in blue, that if 0, 5 is on f of x, then 0, 1/5 is on 1 over f of x. And all I did there was I took the y value and put it under 1. That's it. Now, I would like to keep going with my technique. So we've drawn f of x. Step one is done. To draw the vertical asymptote, because we drew f of x, typically we draw x-intercepts. That's going to be our vertical line right through the x-intercept. So the vertical asymptote is done. Now, drawing your IPs, I do want to put beside this that this is when y is equal to positive or negative 1 on f of x. And I'm going to ballpark this a little bit. Y is equal to 1, I'm going to say right here, and I'm going to say right here. Now, we are going to deal with a question when they want us to actually solve for the invariant points. I do want to maybe do one of these quickly, that if I wanted to find out where that rightmost invariant point was, is I would say, okay, f of x is equal to 1. That means that 2x plus 5 is equal to 1. I'm going to subtract the 5, so 2x is equal to negative 4. Divide by the 2, I get that x is equal to negative 2. Now, that means the point negative 2 comma 1, which is roughly where I draw it, I think, is on the original. Negative 2 comma 1 is also on 1 over f of x. And I think it's important to see how that works, that if I want to verify that, then I just need to put the same x value in. So 1 over the function evaluated at negative 2 would be 1 over 2 times negative 2 plus 5, which is 1 over negative 4 plus 5, which is 1 over 1. That's invariant. That's still 1. And we get that on either side. All right, that's step 3. Our invariant points are drawn. Number 4 is to draw the reciprocal. And that takes practice. That takes using your calculator. I want to talk through, there's really 2 ways of doing this that I really like, is if we look at this invariant point and the behavior to the right. As I move to the right on my original function, the y value gets larger and larger. On my reciprocal, my y value is going to get smaller and smaller, but it's never actually going to hit 0. And if we're drawing the vertical asymptote, we could actually draw the horizontal asymptote right away as well. And that's going to be at y equals 0. Because if I take 1 and divide it by 2x plus 5 with any x imaginable, a number, you cannot get 0. And that's why our horizontal asymptote is there. Now, if we look at that rightmost invariant point towards my vertical asymptote, what's happening on the red line is that my original function is getting closer and closer to 0. So my reciprocal approaches positive infinity. All right, on the left side of the asymptote, if I look from this invariant point towards the x-intercept, my original function approaches 0, so my reciprocal goes down. Now it's going down to negative infinity because my original function is approaching 0 from the negative side of the y number line. To the left of that number, my original function is getting larger and larger and larger in the negative direction, so my reciprocal approaches 0 as well. When in doubt, graph it out. Using your calculator to kind of enhance some of the work that we can do on paper is a really important thing in Dash 1 Math. And those techniques are not going anywhere, so we have to make sure that we push them as much as possible.